Okay, for the position analysis, we did the sequential analysis. That is, we usually use triangles and the sine and cosine theorems in order to obtain results. So let me share the screen and show it to you. For example, if you have a 4-bar mechanism like this one, what we do is, let's say, let's give names, let's say A0, B0, AB. What we do is the following. We divide this into 2 triangles, like this one. This is not a good one. Like this one. So we have 2 triangles here. A0, A, B0, and the triangle A, B, B0. Okay. Now, in all of these, this is, let's say we have theta 1, 2. We know A1, A2, A3, A4. If we call this S, this distance AB0S, we can sequentially solve for these triangles, okay? And also we have, let's say, theta 1, 3 and theta 1, 4 here. Okay. What we want to do is, given theta 1, 2, find theta 1, 3 and theta 1, 4. Okay, that's the idea. That's the position analysis. So what we do here is we define certain quantities, like this quantity is defined as the mu transmission angle. I don't remember. One of them, this is it's called, I think it's called phi prime. This whole thing is called phi, and this is called psi, I think. This is psi, let's say. Now, in these triangles, you see A1, A2, and theta 1, 2 is known in the first triangle, which means that we can solve for S and phi prime, right? Now, S is known now. We can go and solve for A1, 3 is known. What else is known here? S is known, A4 is known. So 3 sides is known, so we can determine the angles. And once you determine the angles, you can determine the theta 1, 4 and theta 1, 3. It shouldn't be too difficult. Actually, I showed that to you. Let me just write down the results, although it's not very short. Let me just write it down for once. For example, we had theta 1, 4 is simply, it is phi minus psi, and theta 1, 3 is theta 1, 4 minus mu. We have mu is equal to plus minus cosine inverse of something like this, where S can be determined from cosine theorem, A1 squared plus A2 squared minus Okay, what is left here? Phi, I guess, or phi prime, if you like. So, what we do is the following. We first, there is one more thing. Phi is pi minus phi prime. That is pi is, so phi is this angle. This is phi. I don't know how to show it. This is phi. So pi. We start from here. This is step 1. This is step 2. This is step 3. For step 4, 5, 6, and 7, basically. So out of using an algorithm like thing, you can solve for the quantities theta 1, 3 and theta 1, 4. One thing I showed you is that this plus minus corresponds to the two positions of the same mechanism for a given theta 1, 2. That is, one position is this one. The second position is, let's say, this one of the same mechanism. This is called the cross position. This is just a review of what we have done for four-bar mechanism. This is the sequential solution. Then I solved the inverted slider crank mechanism for you. And that was the end, I think, the last time, with the same approach. So today I will do something a little bit more complicated. Again, the sequential solution. This will be the something we have seen, the quick mechanism. We will try to analyze this sequentially. Let me try to draw lines. Yes. So let's define, first of all, our links. The crank is 2. This slider, this is 3. This long thing is auto, O4A is 4. This one is 5, and this is 6, the other slider. So the idea is that this is the crank rotating. the way we define angles for this case, it is possible to do it otherwise, but let's define it this way now. I don't know, somehow it is defined like this in this problem. It is possible. This angle is theta 1, 2. This angle is theta 1, 4. And this angle is theta 1, 5. Okay, those are the unknowns. Then we have certain distances here. This distance is defined as S16, which is an unknown, okay? And then this distance is also an unknown. That is a variable rather. S34, 3 sliding on 4. Okay. So given is theta 1, 2. That's the variable. We want to find theta 1, 4, theta 1, 5, S34, S16. Okay, 4 unknowns. And we have 2 loops, as you know, in this mechanism. So it can be done. It shouldn't be too difficult. And also we have the link lengths. A1 is, let's say, O2, O4, with this distance. And supposedly they are on the same line. Then we have A2 is O2C. A4 is O4A. And you have A6 is O2D. What is that? Oh, this is D. So this distance between O2 and D is called A6. There is one more, A5, which is AB, as you can guess. Okay, these are fixed.
Point B is an arbitrary point that you fix everything, right? Just for reference.
No, it is the perpendicular, well.
So it's a reference point.
It is a reference. It actually doesn't exist there, but we construct it there, but we need that, okay, in order to analyze the mechanism and also write the loop equation. It is a fictitious point, okay? So let's try to analyze this mechanism. So in the triangle, we look at the triangle first, the simpler one, triangle O2, O4, and C. That is this triangle over here, which is something like this. You can draw it with lines. It's much easier. Okay. Okay, here we have, this is A1, this is A2, and this is S3, 4. What else? This external angle is theta 1, 2. And this angle is theta 1, 4. Theta 1, 2 is known here, okay? If you know theta 1, 2, you know the complement angle to theta 1, 2. So you can find S3, 4, for example, here from cosine theorem. A1 squared plus A2 squared minus 2A1, A2 cosine. Now, it is pi minus theta 1, 2, whatever that is, to the power 1 over 2, right? And then the theta 1, 4 angle can be found from either the sine theorem or the cosine theorem, cosine inverse of, let's say, A1 squared plus S3, 4 squared minus A2 squared divided by. Okay. Then, let's go. If I go there, we will lose something. Let me write something here. There's a geometric relationship. Well, we can write the following expression. The cosine of A4 times cosine times theta 1, 4 is the vertical distance, this distance, okay? From O4 to A, the vertical distance. It is equal to, this distance is A1, although it doesn't look like it, this is A1. And then you have, this distance is A6, and then you have A5 times cosine theta 1, 5. That is the vertical distance of this A5, okay? So it is like, it is this. The whole thing is A4 cosine theta 1, 4, but we divide it into, from here to here is, let's say, A1. From here to here is A6. And from here to here, it is A5 cosine theta 1, 5. So this is O4, this is O2, this is B, and this is A. Okay. And the whole thing, if I can write it here, is A4 cosine theta 1, 4. Okay, you can see that, right? From which, if you look at it, what in this equation, what is unknown? A4 is known. What? All A's are known. Theta 1, 4, we already solved for it. Theta 1, 5 is unknown in this equation, so it can be solved. So let me go to another page. Therefore, I can write theta 1,5 is equal to cosine inverse A4 cosine theta 1,4 minus A1 minus A6 divided by A5. I just solved that equation for theta 1,5. One more thing. Let me, well, maybe I should write it here also, if I can. Let me write it here. I can write the same thing horizontally, or yes, horizontally. A5 sine theta 1,5, which is this distance, okay, is equal to A4 sine theta 1,4, which is the horizontal distance, plus plus S16. If it is not very clear, let me try to draw this also. Where to draw it, that's the problem. Maybe I can just erase a few things here. This is the horizontal thing, okay? On one hand, it is A5 times sine theta 1,5. On the other hand, we have A4 times, this is A, this is what? This is D, actually. Well, okay, it should be, this thing should be here, okay? O4 should be on the same line with D. It should be on the vertical. So this is A4 sine theta 1,4, and this is S16, okay? And this is D. So this is what we are writing here. And look at it, now we have solved for theta 1,5, theta 1,4 was known. So only unknown is S16. So S16 can be solved from this equation, which can be written as S16 is equal to A5 sine theta 1,5 minus A4 sine theta 1,4. So these are also solved here. One thing is missing, maybe. No, nothing is missing. Let me just check. We erased it, but we had solved for S34. We had solved for theta 1,4. And we solved for, I erased that part. We solved for theta 1,5. We solved for S16. So everything is known here. No problem. Okay. Any questions about this? This is a two-loop system, but we didn't really use the loop, but we could have. There is no, this is not a very general thing. You just have to look at the triangles, the geometric relationships, and try to construct your answer from the geometry. And note that we don't really use the loop equations or complex numbers here at this point, at least. So we solve sequentially. We have our solution sequentially, like in a computer algorithm. which is okay, I suppose. Do you have any questions about this? Okay. If you don't, then I will continue. I will, as I said, we didn't use complex numbers here, but we could have. Actually, that gives us, using complex numbers and loop equations, gives us a kind of a more systematic way to do the position analysis. So let's look at that position. Let's say we have again our famous 4-bar. So as you might remember, our loop equation was A2 e to the I theta 1, 2 plus A3 e to the I theta 1, 3 was equal to A1 plus A4 . So we were just adding up vectors like this vector plus this vector is equal to this vector plus. Sorry for my poor drawing. Okay. Well, the idea is this is not the only possible. Well, there is another, the same mechanism can assume another position, which I will draw by here. There is a mirror image of this mechanism, which will be this one. I don't know if I could draw it well, but I guess you get the idea. And the angles here are, this is minus theta 1, 2. Okay. And this angle is, well, we are measuring the same angle clockwise, as you see. Here it is also minus theta 1, 3. And here it is minus theta 1, 4. Okay. That is, the same equation is correct for minus theta 1, 2, minus theta 1, 3, and minus theta 1, 4. So we can write the complex conjugate of our mechanism equation, and that will also be correct. That is A2 e to the I theta, sorry, not minus. Okay, so it is exactly correct. So, and this thing is the mirror image, let's say, of the same mechanism. Now we can, using these two equations, now we have two complex equations, we can eliminate a few things. For example, I can write them, well, okay, well, what we want to do, let's say, we want to solve for theta 1, 3 and theta 1, 4. From these equations, I can eliminate theta 1, 3. How do I do this? Let me just do it on a page, another page. Eliminate, let's say, theta 1, 3. And the way we do it is we leave A3 e to the I theta 1, 3 term alone. So it becomes A1 plus A4 e to the I theta 1, 4 minus A2 e to the I 2. And also you have A3 e to the minus theta 1, 3 from the complex conjugate plus well, I guess you have the right to draw things here, but don't. Um, okay, now the whole idea is we take this and multiply. Well, we get a kind of a complicated expression, which is the following: A3 squared e to the I theta 1, 3 minus theta 1, 3, which is nice because this becomes a 1. So we have A3 squared here is equal to, but unfortunately this one is not very simple. A1 plus A4 e to the I theta 1, 4 minus e to the I theta 1, 2 times A1 plus A4 e to the I, not I, minus I, 4. Okay, now we will, well, multiply all these terms and get a complex expression, but just here remember the following before we go on. Cosine theta is e to the I theta plus e to the minus I theta over 2. Okay. This is again Euler's identity. So once you do that multiplication, you get the following things. this whole thing equals 0. Okay? Well, this equation, once you multiply everything by each other, eventually you are going to get the following expression. Okay. Okay. And if you divide by A2 times A4, you are going to get we divide by 2A2 minus A1 A4 cosine A1 plus equals, we can write cosine okay. Now we can call these terms something. Let's call this whole thing K3. Okay. Now, although this looks too complicated, you know, once you program these things in a computer, it's not a big deal after all. It is, you know, it is doable. You don't do the real work, the computers do it for you. So you can basically solve for well, we are trying to solve for theta 1, 4. Now our equation becomes the following. K1 cosine theta 1, 4 minus K2 cosine theta 1, 2 plus K3 equals cosine theta 1, 4 minus theta 1. This is called the Freudenstein equation. I guess it's to honor the person who first found it. Well, the good thing about this is that this has an analytical solution. That is, you can directly solve for theta 1, 2. Although it's not very easy, it can be done. So what we do here is this cosine theta 1, 4 minus theta cosine theta 1, 2. We write it as cosine theta 1, 4 cosine theta 1, 2 minus, we say, sine theta 1, 4, sine theta 1, 2, okay? No, okay. So there are those expressions. I don't know whether to write this, but these identities are as follows. Sine theta 1, 4 is equal to 2 tangent theta 1, 4 over 2. So those are half angle terms. Now, if you substitute these into the following equation, Freudenstein's equation, you know that it becomes very complicated, but it becomes the following. Let me just write it down. A tangent square theta 1, 4 over 2 plus b tangent plus c equals 0. Okay, where a is equal to cosine theta 1, 2 plus k3 minus k1. E is finally C is this is all actually this is all in the book by Eres Hoca. And from here, this is a quadratic equation. If you call tangent square theta 1, 4 as x, you can, this is a quadratic equation to be solved for x, from which you can solve for theta 1, 4. Let me just give you the solution. 2 times tangent inverse of So we solve for theta 1, 4, okay? It is a long process, but we got a real solution, analytical solution. So what we did was we eliminated theta 1, 3, and we got an equation in terms of theta 1, 4, and which we solved. And you have to do the same thing similarly. So a similar solution is possible for theta 1, 3 as well. But I'm not going to do it. It's already took too much time. But you understand the idea. But I hope you understand the idea. It is complicated. It looks complicated. But it is always, once you get the correct solution, if you program it on a computer, well, it is actually not so difficult to do, okay? If you correctly program it, you will get the correct solution.
Isn't the minus b plus minus all brackets? Isn't it like the quadratic?
It is, because this is a quadratic equation. Obviously it is. This is, let's call this x squared. This is x. Okay? That's all. That's why we have here the following expression. Well, the thing is, these equations look very complex and very intimidating, but eventually you will, once you solve it, you get the result. It's not a, you know, extremely difficult thing to do. It was done first by a person, then it can always be done. Once you program it on a computer, you don't have to do it by hand. Okay, let's take a break here for a while. We'll be right back. There was a question, but it's too late. Okay, so let's take a break. Okay, so for four-bar mechanism, this is, although it's very complicated, we can get a kind of an analytical solution. And note that this is not sequential, okay? The previous method which we used was sequential. That is, we solved for S, then we solved for this angle, that angle, mu and phi and psi and so on. Then finally, we solved for theta 1, 4. Here we have an equation. Although it's very complicated, we have an equation that solves for theta 1, 4 directly. That's the main difference. Let me do something similar for a slider crank mechanism with some eccentricity. So let's say you have a crank and a slider like this, and then sorry, slider is this one, the connecting rod. Now, so S14 is an unknown. And then this distance, which is a fixed quantity, is the eccentricity E of the mechanism. And we have the angles. Crank angle is theta 1, 2. And this angle is theta 1, 3. So this is an eccentric slider crank. Given is theta 1, 2. You need to find theta 1, 3 and S1, 4. Okay, we write the loop equation and we will solve it through the complex numbers. A2 e to the I theta 1, 2 is this vector. So our vector equation is like this is equal to okay, and we can write the complex conjugate of this one, e to the minus I theta 1, 2 minus IE. Whenever we see I, we put a minus I, okay, because we are taking the mirror image of the mechanism, that's important, plus okay, so this is our equation. These are our equations. We want to, what? To, not, this is not just SS, we said S14, right? We want to solve for S14, we need to eliminate A3. So you can write A3 e to the I theta 1, 3 is equal to minus S14 minus IE plus and also we have A3 e to the minus plus IE plus IE. We take these and once we multiply this, but e to the I theta 1, 3 is cancelled, so we don't write it. I3, so yes. Which, this one? This one? This one?
No, there's like, in the second equation is down.
This one?
Yeah. Theta negative.
Oh, okay. This should be it. Yeah. Okay, thank you. Is equal to. Okay, now we multiply everything here. Let's do that. It is S14 squared is these terms multiplied plus A2 squared plus E squared actually minus now the cross terms S14A2 e to the I theta 1, 2 plus e to the minus I theta 1, 2 is plus you have IEA2 something like this. Now, these can be simplified. This term is 2 cosine theta 1, 2. And this term is 2i sine theta 1, 2 from Euler's identity again. So, using these, we get rid of the complex numbers in our equation, as we should, okay? Because we are dealing with a real thing here. We shouldn't be eventually be having complex numbers in our equations eventually. Let me write this down again. So, what we will have eventually is S14 squared minus 2A2 cosine theta 1, 2. Cosine theta 1, 2 is known, so it's not a big problem. Not S4, S14. Plus E squared plus A2 squared minus A3 squared E A2 equals 0. So this is a quadratic equation in terms of S14, as you see. So it is solvable. S14 is equal to minus B, which is this one, A2 cosine theta 1, 2. No, this is minus B over 2. So we have a closed form solution for S14, as you see over here. Okay. So much for S14. S14 is solved now. Now we need to solve for example, theta 1, 3. Okay. Theta 1, 3, where is that? We can do it. Actually, we have done it previously using sequential numbers, but let's try to get rid of S14 and then solve for our equation. If you leave S14 alone, 2 e to the I theta 1, 2 minus 2 T. This is the regular loop equation. The complex conjugate of this is e to the minus I theta 1, 2. So we have these. If we divide them, actually, as you see, we just get rid of S14 because, well, this sides cancel and it becomes a 1. And then we can equate these terms to each other. So what we get will be A2 e to the 2 plus A3 e to the minus I theta 1, 3 plus IE is equal to A2 e to the I theta 1, 3 minus 3 minus IE. Okay. So I can collect the terms, A2 terms, e to the I theta 1, 2. Minus e to the minus I. Plus 2. So you have, this one is 2I sine theta 1, 2. This is 2I sine theta 1, 3. And this is 2IE. Now the I terms nicely cancel out from everything. And what we are left with is, let me just add it here, A2 sine theta 1, 2 plus A3 sine theta 1, 3 plus E, well, minus E actually. Equals 0. Actually, we had obtained this equation in the sequential analysis or using the geometry. So theta 1, 3 is simply sine inverse of E minus A2 sine theta 1, 2 over A3. That's all. So that's the result. And for the S14, we had obtained the result here. Okay. Is there anything that's unclear? So on the other hand, there are other possibilities, like in the slider crank. You can write, for example, the horizontal distances like you can write S14 is equal to A2 cosine theta, A2 times cosine theta 1, 2, and A3 times, again, cosine theta 1, 3. Add them up. And then you can write an expression for the vertical. And from there, you can just solve as we have done before. It gives you the same thing. Okay. Let me do a position analysis again for a kind of simple inverted slider crank here. This is well, this is its position analysis is rather simple, as we will see, because there is a simple triangle here, which we can, let's say, which we can call X if you want to. So the input being theta 1, 2, the variables are S43, which is X, which we can call X, and theta 1, 4. Now the position analysis is really simple here, because this is A1, A2, and theta 1, 2 is known, as you see. So in this triangle, we have this is A2 is known, A1 is known, and this is theta 1, 2 is known. So this triangle is determined. We can find this X and this whatever, pi or something, or this theta 1, 4. But we will try to do it in the long way, using complex numbers, so that it will be well, it will just illustrate the complex number idea here. So the loop equation is A0A is equal to A0B, A0B0 plus A0. I will write the same thing. Leaving this term alone. Complex one because of it. So we will multiply these. Once we multiply, we will get the following expression. X squared is equal to a squared, so a2 squared plus a1 squared minus a1, a2, e to the I theta 1, 2 plus e to the minus I theta 2. Okay, so this is 2 cosine 2.
Then the question, if you can go back to this 1 second.
Yes. So you simply write x squared is equal to a1 squared plus a2 squared minus 2a1 a2 cosine theta 1 2, right? Which is, what is this? This is the cosine theorem for the triangle, right? I told you that this is simple. We do a simple thing in a complicated manner, actually. You can solve for theta 1 4. If you like.
So why did we go through the complex way to just achieve this?
Well, we went through the complex way to illustrate the complex number concept. Okay. In order to solve for, let me see, let's go back. Theta, we solved for what? X or S for 3. In order to solve for theta 1 4, actually theta 1 4 can be directly solved from sine theorem, but we can, in order to do that, we can also, what can we do? We can divide, for example. So again, we get rid of x's. So let's say this is 1 and this is 2, okay? It might get a little bit complicated, but let's try to do that. So what you get will be x's are going to cancel. E to the I theta 1, 4 plus theta, well, minus is a plus theta 1, 4 is equal to 2 e to the I theta 1, 2 minus A1, 2 e to the this might get too complicated, I'm not sure. Actually, there is no direct way to solve for theta 1, 4 from here, I suppose. Probably there is an easier way. First of all, the easier, very much easier way is use the following. If you look at it, well, let's keep it here for the time being. I will tell you later. For example, you can do A2 over sine, let's say, pi minus theta 1, 4 equals over theta 1, 2. I'm just making a simple thing more complicated here. Let me see. Okay. There is one more mechanism. Hangisinde? Which one? Burada mı? Okay. No, it is it is the okay. I divided the minus, so it's a minus and the minus, it makes a plus. Okay. Here I divided this one to this one, so e to the I theta 1, 4 divided by e to the minus theta 1, 4 is a plus theta 1, 4. Yeah, but this, it should be possible to solve from here and get the result, but it doesn't look like it is, simple. Probably it will take some time to do it. So I skipped it, and there is a simpler way of doing it. Okay. I don't know how much time we have, probably not much. I want to solve a problem, one more problem before we leave this topic, but probably I'll just have to start and then do it the next time. So let me start at least for now. This is there is no this is rigidly connected. Okay, this is the problem. It is again an inverted slider crank, but a kind of a strange one. First, we have to understand the link 3 is the piston inside, moving inside the this link 4. Okay. And link 4 is rigid here at point B. So there is no revolute joint at B. Again, certain things are given. A0, B0 is called R1. A0A is R2. B0B is R4. And this angle is 90 degrees. The angle of B0, BA is 90 degrees. Okay. And actually certain numbers are given here. This is 8 centimeters. This is centimeters. The question is, theta 1, 2 is not given here. Find theta 1, 3, 2, and theta 1, 4 for S43 equals 4 centimeters. So this is the input variable. So you are required to find all the possible solutions. Let me just write down the loop equation, then I will stop for today. It is R2 e to the I theta 1, 2 equals R1 plus R4 e to the I. Now, this is equal to this one, R1, plus this one, B0B. B0B is this. So this is A0A is equal to A0B0 plus A0B0, B0B plus B0, there is, it's not called anything.
Are you considering S43 or S42?
No, S43, I kind of, all right, let me just explain. It's B0, it should be BA, but the way I drew S43 is wrong. S43 has to be this. This whole thing has to be S43. It is a variable, right, as you see. Now, why this this R4 e to the I theta 14 is clear, okay, because this is the angle is theta 14. But why do we have this I? The reason is that this BA is 90 degrees to, this is 90 degrees to B0B, which means that we rotate our vector by 90 degrees counterclockwise, and rotating counterclockwise, 90 degrees counterclockwise means multiplying a vector with I. Okay, that's why we multiply it with I. Is that kind of clear? Okay. The next time, I hope I will be able to save this. We will start from here. And continue with this example. And then we will go somewhere else. Okay, that's all for today. Any questions? Yeah, that's later on. Stop there. Anything, anybody asking any questions? No? All right, thank you for listening. Then I'll see you on Wednesday. Goodbye.
İyi günler hocam.
İyi günler.
İyi günler hocam.